So very good morning, students. Welcome to IIT NEET Foundation, our Focus C program by Krishnaveni Talent Schools and the Mastermind Schools. So once again, I welcome all the class 9th students for today's session. As you all can see on the screen, and you are well aware, my subject is physics. We are in class 9th. Today we are going to start a new chapter, that is chapter number 5, circular motion, and we are in the session number 1. So before going for the chapter directly, when you recall about this type of motion, so in our day-to-day life, we'll see so many kinds of motions we discussed already in the earlier chapters. When a body changes its position from time to time, we can call it as motion. It may be linear motion, it may be rotatory motion, it may be vibratory motion, it may be random motion. Depends on the way it is moving. They are named as different kinds of motions which will come across in our day-to-day life. So when you see this circular motion, as you know, a body follows a circular path. Right? Circular path. For example, when you see the watch, wall clock, how the needles will move in the circular path, roundly, and gives us the time for us. Electrons moves around the nucleus in a circular path. Planets around sun in one kind of circular path, that is elliptical. And when you go to the exhibitions or circus, you can see the giant wheels. The giant wheels will move in the circular path about a fixed point with a constant radius. Body will cover the circular path. So among all the motions, why we are discussing only about circular motion? Because there are some special properties are there. There are special applications are there for this type of motion, right? So we'll move to our material part. What we are going to learn about the circular motion, right? So circular motion, we are ready. Chapter number 5. So when you see here, bodies in natural world have remarkable tendency to travel in a curved path. A type of motion in which a body travels in a curved path is called curvilinear motion. Circular motion is a special type of curvilinear motion in which curved path is circular. See, perfect circle, it is moved circular path. This is also there. So many ways the body can move, or it may be like this. This all comes under the curvilinear motions because there is a curve is there. But out of these all types, this is a special case. Circular path is special case. The radius is same at every place. Here see, here there is this radius is different from this radius. Larger, smaller. Here is a larger, major and minor are there. But in case of circular motion, all are same only. The radius is same, and with this constant radius, body will follow the circular path or a curved path. Such kind of motion is called circular motion. Right? There. According to the Newton, again came here, Newton, second law of motion, a change in the direction of motion of body takes place only if some external force acts on the body. So, without application of force, body cannot neither can move from the rest, nor can come to rest, nor change the direction. So, when a body started moving, when force acts on the body, that force makes the body to follow the circular path. Right? Which will deflect the body from its straight line path to the circular path every point of the path. At every point, force is acting and making the body to turn. Otherwise, body should go like this. Random, that is perpendicular. But because of the force acting on that, yes, to create the circular motion in a body with uniform velocity, the force must act normally, instantaneous velocity of the body. See, actually body start from here, should go this direction with the velocity. But because of force, change the direction. Again, change, follows the. So circular motion can be classified in two types: uniform circular motion and non-uniform circular motion. As you know, uniform is nothing but constant, covers same distance in same time. Whereas non-uniform is nothing but opposite to that. It covers the unequal distance in unequal interval of times. These are two types are there for the circular motion. So before going for that, let me show you video on the introduction part of circular motion. Then we'll move to the theory part, right? All these are the examples.
We had to come up with a good excuse to visit Wild Adventures. This place is full of reasons to learn about physics, starting with going in a circle. What if I'm moving in a circle on this ride at a constant speed? How am I accelerating? Anytime an object is traveling in a circular path, it is accelerating because its direction is constantly changing. Now remember, velocity is a vector. It has magnitude and direction. If either changes, velocity changes. And acceleration is defined as a change in velocity. Let me show you an example.
See, observe.
You ever wonder why you can swing a bucket of water like this?
He is rotating. No single drop of water.
And the water doesn't spill out? It's because of centripetal force. It's a word that means center seeking, and it's written F sub c. Centripetal force is any force that makes an object move in a circle.
Very important. As I told, to change the direction of the body, there should be some force. Because of the fundamental acting of force, body will follow the curved path. That force is called centripetal force. We learn in the further. Okay.
There's more than one kind of centripetal force: friction, tension, the normal force, or gravity. And any of these can act as centripetal forces if they cause the object to move in a circle. Here's another way to say it. Centripetal force is the net force acting on objects that keep them moving in a circle. When I swing the bucket, there are two questions. Which force makes the bucket move in a circle, and what keeps the water in the bucket? There's a fine balance here in keeping the water in the bucket. So what forces are acting on the water in the bucket? Well, let's draw a free body diagram of the bucket first when it's at the top of the swing. The force of gravity, F sub g, acts down. Tension, F sub t, acts down on the bucket as well. The force of gravity will act down regardless, but the tension force will always act toward the center of the circle. In this example, the tension force and the force of gravity create the net force, and together they make the bucket seek the center of the circle through the centripetal force. In a free body diagram, you don't write centripetal force per se. You write in the specific force or forces causing the centripetal motion, in this case, gravity and tension. So what forces make up the centripetal force when the bucket is at the bottom of the loop? You can see that the tension force still acts towards the center, and gravity continues to act down toward the earth. So what keeps the water in the bucket? It's the normal force of the bucket on the water's inertia. Tension keeps the bucket moving in a circle. The water within the bucket experiences the normal force from the bottom. This force keeps the water moving in a circle. If we were in the middle of space and there was no gravity, the water would still stay in the bucket as it was swinging in a circle, thanks to the normal force. And what force keeps the bucket going in a circle? Well, that's easy. It's the tension of the rope. Okay, what if there's no rope? For example, what force keeps a satellite orbiting the Earth? It's gravity that pulls the satellite toward Earth and keeps it in orbit. So the centripetal force is Earth's gravity. It's the tether that keeps the satellite orbiting around a central point instead of flying off into space. But keep in mind, it has to be going at a certain velocity to stay in orbit. If the satellite slows, it will give way to Earth's gravity and fall to Earth. So let's take a few circles around this track. The only difference between this and the bucket of water swinging in circles, the bucket of water swings in vertical circles. The circle we're traveling in here is horizontal. But the good news is the same principles apply. So based on that, what forces keep this cart moving around the circular track? Frictional force is at work helping the tires grip the track and keeping the cart in a circular path. Vertical forces on the cart cancel out. The cart is center-seeking, only in the horizontal direction. And how about when you make a sharp right turn and your body is slammed up against the left side of the car? What causes that? Is it centrifugal force? Absolutely not. Turns out centrifugal force is not a force at all. The real reason is explained by Newton's first law. Just like the water in the bucket, your body wants to stay in the same motion, except the go-kart is turning to the right. Your body is resisting the change of the circular motion and wants to continue in a straight line. That's inertia. So the force you feel is the car running into you as it seeks the center of the circular path in which it is traveling. Okay, so let's go back to our rotating bucket of water. We know why the water stays in the bucket. It's experiencing uniform circular motion. That's when an object moves in a circular path at a constant speed.
Water is not falling.
Now, what do you think will happen to the bucket if I were to let go of the rope? What direction will the bucket move? The bucket's velocity is called tangential velocity, V sub capital T, because if tension lets up at any given moment, the object flies in a straight line that's tangent to the circle. So the direction of tangential velocity changes constantly as the object travels in a circular path. To measure how long it takes for the object to go in a full circle, that's called its period of revolution, capital T, or simply the period measured in seconds. Let's go to another ride. Recall from another segment that velocity is a vector quantity. It has direction and magnitude. The magnitude of v is speed, which is constant for uniform circular motion, but we will call it our tangential velocity, since this speed and the tangential velocity magnitude have the same value. This ride does one full circle. The distance traveled is called the circumference and is calculated by multiplying the radius by 2 pi. And the time it takes to make a full circle is called the period. You write that as capital T. The tangential velocity of an object traveling in a circle is the distance around the circumference divided by the time it takes to travel around the circle once, which is the period T. And remember, if an object is moving in uniform circular motion, it is accelerating because its direction is constantly changing. This is called centripetal acceleration. Centripetal acceleration is equal to the tangential velocity squared.
So this will come in the next part, but just we should know about what is the circular motion. And one more is there.
He knows a lot about the science stuff. Professor Dave explains.
We've examined a lot of linear motion up to this point, whether horizontal, vertical, or at some angle. But there are a lot of objects that follow circular paths of motion. This type of motion is accompanied by an entirely different set of equations. So we have to learn these if we want to approximate the motion of the planets as well as a wide variety of earthbound objects.
Planets around the sun.
Consider a Ferris wheel. As the wheel turns, the cars exhibit circular motion because they revolve around a single axis of rotation, which runs through the center of the wheel perpendicular to the plane that contains it. The cars move around this axis with a constant radius, so they trace a circle as they move, since a circle is the set of all points equidistant from some central point. To describe the speed of the car, it is common to discuss the tangential speed, because the inertia of an object causes it to try to maintain a straight line path. This is the speed of the car along the tangent line at a particular instant. If this tangential speed is constant, we will call this uniform circular motion. The
important. There are two types I told you. Motions are two types. Circular motion, uniform or non-uniform. Uniform is constant speed.
Tangential speed will depend on the distance of the car from the axis of rotation. If you place a sticker on the wheel very close to the center, it will complete one revolution in the same amount of time as one of the cars. But the sticker will travel just a short distance that you could trace with your finger, while the car travels much farther, all the way along the edge of the wheel. Since speed is distance over time, a shorter distance covered in the same amount of time must mean a slower tangential speed. This seems counterintuitive, since the wheel is one object, but that's why we can also discuss angular velocity, which we will learn about later. The uniform circular motion of the car happens because of a constant centripetal acceleration towards the center of the wheel. At any given moment, the car has a velocity vector that is tangent to the wheel, and while the magnitude of this velocity will not change, the direction is constantly changing, and any such change in velocity can only happen due to some acceleration. The centripetal acceleration will always point towards the center of the wheel, which will in turn continually pull the direction of the velocity vector towards the center of the wheel. This is what produces the circular motion, as though the car is always trying to move towards the center of the circle, but never makes it there because of its tangential speed. Centripetal acceleration is given by tangential speed squared over the radius of the path, so this value would increase if the car were to move faster and if it were to sit closer to the center. We know from Newton's second law that if an acceleration occurs, there must be some force present to produce it, and centripetal acceleration is generated by the centripetal force. Centripetal force is simply centripetal acceleration times the mass of the object, since F equals ma. So we can describe centripetal force by simply...
So these all will come later, just we are only introduction about the centripetal, right? So when you see here, circular motion, what we discussed, we started the circular motion. Circular motion is that but motion of a body around a circular path. So actually body supposed to move in the tangential path, but because some force acts on the body to make the body to move in a circular path, whether it may be gravitational force, or it may be frictional force, or it may be muscular force, no matter. Some force acts on a body which makes the body to revolve. For example, Earth, you can see, Earth is following the circular path because of the gravitational force, or all the planets. Similarly, electrons revolving around the orbit because of the nuclear force, which acts as a centripetal force. So in that, when the body is moving in a circular motion, it can be either uniform circular motion or non-uniform circular motion. You can see some examples are given. When a body moves along the path with constant speed or uniform speed, its motion is called uniform circular motion. Example, motion of a satellite around the Earth. Motion of the second's hand in watch. Wall clock, you observe carefully, the second hand moves uniformly. Right? Means for every 60 seconds, it makes 1 minute. Means any time. That means that is moving uniformly. Motion of the electrons around the nucleus. Satellite which we are launching from here, it also moves around the orbit constant speed. Means, for example, for one revolution it takes 10 minutes. Second also 10 minutes. Third also 10 minutes. Then only you can say it as a, just now you have seen, he kept the sticker. Why you kept the sticker? To observe how much time it will take to complete one revolution. Right? So since the force is always right angle to the displacement, therefore no work is done by the force on the particles. So you know right angle 90 degrees. When 90 degrees is there, work done is 0. W is equal to Fs cos theta we have seen. When theta is 90 degrees, total work done is 0. So as there is no work done on electrons or on satellites or on the second's hand, they move continuously around the same path, same time. Right? Hence, its kinetic energy and thus speed is unaffected. So as there is no work is done on the particles which are uniform circular motion, they move constantly, and such a motion is called uniform circular motion. The best examples are motion of a satellite around the Earth, motion of the tip of the second's hand. You can see watch, hand watch or wall clock. You observe carefully the second hand. It moves for a complete rotation with 60 seconds, 1 minute. Again 1 minute. Again 1 minute. Same either today or tomorrow or day after tomorrow, until unless the watch is dead or cell is completed. That is called uniform. It moves uniformly and giving us time. Why it is moving uniformly? Because there is no work is done. It is not moving from the particular point. Because it's moving in the perpendicular. The force and the displacement are in the right angle. Right? Then the second category, non-uniform circular motion. When a body moves in a circular path with non-uniform speed, is called non-uniform circular motion. What is non-uniform speed? Speed changes. When speed changes time to time. So, speeding up flywheel of a motor. Any motor wheel, if you see, you can speed up. Sometimes you start slowly and then pick up the speed. So, speeding up of flywheel in a motor is the best example for the non-uniform circular motion. Right? So, circular motion is the motion of a body around the circular path about a fixed point. It can be either uniform or non-uniform, depends on the speed. The speed is constant, motion is uniform. If speed is variable, motion is non-uniform. Okay? Now, variables of circular motion. See, motion will use some common words. In motion, we'll use the word displacement, distance, velocity, acceleration, retardation, speed. These words will change. The terminology changes in case of circular motion. That is called variable. See, displacement and distance. First, the radius vector, very important term. A vector pointing from fixed point to instantaneous position of the particle in a circular motion. Suppose say it is the center. From here, this is called radius vector. This is called radius vector. It is constant everywhere in the circular motion. The radius is same everywhere. Such radius is called radius vector. Why you are saying vector? Because it is always the specific direction. It follows a specific direction to make the circular path. Right? So when a particle moves in a circular path during the time t, as shown in the figure, from position A to B, it came from position A to B here. Right? One side. So let me. So OA, it moves from OA to OB. Correct? Position B. We see that the magnitude of the position of vector that is equal to the radius of circle remains constant. So this radius is same with this radius, same with this radius and all. Okay. We see the okay. The direction of position vector radius changes from the time to time. So it won't stay there, it moves from point to point and changes. That is called a constant radius, which makes the body to move in a circular path is called radius vector, which is the one of the important term in the circular motion. Next, generally displacement we call it as a angular displacement. Angular displacement. The angle turned, see what happened here? Same only, OA to OB. OA to OB, it makes some angle here in some time. So this angle is called, this displacement of the body from OA to OB is called angular displacement, because displacement is change in position. But this change in position makes some angle. Okay. So the angle turned by the moving body in a circle from some reference line is called angular displacement, which is measured in units, radian or degree. We can convert the radius into degree, right? We'll learn in the, already we learned in the first chapter, mathematical physics, right? So it is sometimes also specified in terms of fraction or multiples revolution. 2 pi radians is equal to 360 degrees for one revolution. When complete body complete one revolution, it is 360 degrees, which is also called as 2 pi radians. 2 pi radians or 260 degrees, 360 degrees. Right? The direction of angular displacement of bodies, circular motion, can be given by which direction body is moving. What is the direction of displacement? easily you can understand by the right hand rule. Just right hand fingers. You can keep the thumb, folded fingers and thumb like this and see how it moves in circular path. Like this you can move. Starting from one point, if you keep on moving this direction, the thumb direction will show the direction of the displacement. It states that if a curling fingers, this is all the four of right hand represent the sense of rotation of the body in circular path, then the thumb held perpendicular to the curling fingers indicates the direction of angular displacement of vector. First we are like this, right? Keep moving, keep moving, keep moving, keep moving. This thumb indicates the direction of displacement, right? So the rotation is represented by this. The circular rotation is represented by curled fingers or folded fingers, whereas the direction of thumb represents the direction of angular displacement. The radius is constant, that is called radius vector, right? Very interesting, that is right hand rule. You can do with your right hand also, it gets same. Okay. So next comes displacement. Some important terms are given in terms of so the shortest distance between the initial point and final position, the common particle is displacement. The change of position of vector or displacement of particle position A to B is given by the referring figure. So this same circular point we have taken. We taken this out, separated, and we are kept here. From that you can calculate the formula for the angular displacement. Right. So for our standard is not required. Simple formula is there. How to find out the distance. Then angular velocity. The velocity is nothing but displacement by time. Angular displacement by time here. Angular displacement by time. Angular displacement is what? Initially, a simple way I explain. No need to go for complicated. Right. So see, initially θ1 is the angular displacement. It moved to θ2. So change in displacement is θ2 minus θ1 by change in time t2 minus t1. Displacement time is the velocity. That is called angular velocity, which is represented by omega. Right, omega. Change in displacement by change in time. Or you can write d theta by dt. Same like velocity. Time only, 1 by time. So radians per second or degree per second is used for angular velocity. Right. Then angular velocity is represented by omega, which is rate of change of angular displacement. Whereas linear velocity is nothing but rate of change of displacement. So what is the relation? Very important thing you remember is relation between those two. Relation between linear, this is very important for us. You remember this formula, no need of derivation for us. V is equal to R omega. V is the linear velocity when a body is in linear motion. Omega is the angular velocity. R is the radius of the circle. So this is the relationship between both linear and angular velocity. As we get from the formula, same only. From this we got. From this omega is equal to, just now you have seen, displacement by time. Right? Displacement by time. So from this AB you will get, what will you get? Before that, omega and omega t. So substitute here. In place of angle theta, you can substitute this one. We'll get the R omega. V is equal to R omega. V is the linear velocity, R is the radius vector, and omega is the angular displacement, angular velocity. Linear velocity, angular velocity. Angular velocity is nothing but in a body is in circular motion. Linear velocity is nothing but when body is moving in a linear path. So the relation is very, very important for solving the many problems. V is equal to R omega. Right. So further going for the next one, there are a few more terms are there. First we see radius vector, then angular displacement, then angular velocity, then comes change in velocity, time period, how to calculate, frequency, very important, angular acceleration, right? All about the uniform velocity, circular motion. Now, in non-uniform circular motion also, we have different types of terminologies. Then we'll know about what are the force, which force is responsible for the body to move in a circular motion. That is centripetal force, centripetal acceleration, and few definitions and formulas. How these equations of motion changed. We have seen equations of motion. V is equal to U plus AT. S is equal to UT plus half AT square. V square minus U square is equal to TAS. These can be changed in terms of circular motion. See, linear motion, this is the formula. Right? The same formula changed into the circular motion in different way. Right? In place of V, use the omega 2 is equal to omega 1, U plus omega 1. You can write like this. In case of angular kinematics, equations are retarding motions. Retarding means minus. Like that, same formulas, the four formulas can be written in the, one is in the circular motion, other one is in retardation motion. Accelerated motion, retardation motion. Very interesting this we learn in the coming days, coming class, next class when we meet, we learn about the remaining part of the remaining terms followed by the equations which are very much helpful for us to solve the many problems. Then we come across again centripetal acceleration, centripetal force, so many things are there, right? So we learned today about the mainly circular motion, what is the circular motion and what are the terms related to circular motion and what are the two types of circular motions, that is uniform circular motion and non-uniform circular motion, right? Okay, so once you go through a complete theoretical part, maybe related to your textbook also. So that's all for today. Thank you, students. Have a wonderful day. Thank you.